Zeal Education Society, redefining excellence.
Welcome back. We'll continue our topic of scalability. As we have already seen, a cost optimal parallel systems has an efficiency of theta 1. So we can easily say over here that the scalability and cost optimality are both related to each other. When you're talking about a scalable parallel system, it can always be made cost optimal if your number of processing elements and the size of the computations are chosen appropriately, and this stands true when you have given a problem size, varied problem size on your varied parallel systems. Let's take an example of addition of numbers we have already taken. Let's take an example of weather forecasting. As I've already said you that when you're talking about weather forecasting, you are actually talking about how what is the pressure for a particular region. You are calculating the pressure, wind pressure on an ocean. You are calculating a particular region and you are giving it to processing elements. Say 1 square meter is the amount of space which is designated to every processing elements. As you increase the area by 1 square kilometer, so as you are supposed to increase the processing elements or processors. If you maintain this, say I increase my area by 5 square meter, I need to increase my processing elements by 5. So if I am maintaining the area on which the computation weather forecasting is supposed to be done and the number of processing elements which are required to handle it, if I am maintaining it, then I can say that I can have a constant efficiency of a system and in fact the scalability, and that system is called as a scalable system. Let's talk about an iso efficiency function of scalability. I've given you a small glimpses of iso efficiency function earlier also. Let's talk in detail now. When you're talking about an iso efficiency function, so for a given problem size, as we increase the number of processing elements, the overall efficiency of your parallel system goes down for all systems. But for some systems, the efficiency of parallel system increases if the problem size is increased while keeping the number of processing elements constant. So we have already seen earlier that as you increase the number of processing elements, okay, so efficiency, there will be a dip in efficiency for your parallel system. But there are some cases or systems where the efficiency goes, at a constant space, even though the problem size is increased and your processing elements remain, number of processing elements for your parallel system remains the same. So as you can see in the figure over here, you have two figures, A and B. So there we can see a variation of efficiency. So we have a graph on y-axis, we have efficiency, and on x-axis we have the number of processors or processing elements used for a parallel system. So as the number of processing element is increased in figure A, for a is increased, and so as your problem size also increases. So look over there, as the problem size is increased for a given number of processing elements, the phenomena is illustrated by, you, in the first figure you have fixed problem size, okay, and the second figure you have fixed number of processors, and the problem size is denoted by W. Over here you have in figure B, you have x-axis, that is problem size. As your problem size is increasing, your efficiency is also increasing. So the phenomena is illustrated, which is illustrated graph B, is not common to all parallel systems. So what is the rate at which your problem size must increase, with respect to the number of processing elements, so that you keep your efficiency fixed? That is the thing which need to be answered. What is, so this rate generally determines the scalability of a system, and the slower the rate, the better it is, because as you increase the problem size with respect to the number of processing element, so your efficiency should increase gradually. It should increase gradually. There should not be a drastic change in efficiency from when you're speaking about efficiency context. If it is gradually minor, to some extent, in a minor extent it is increasing, there you can say that we are going on right track. So before we formalize this rate, we should define what do you mean by a problem size, which is W, as and your asymptotic number of operations which are associated with the best serial algorithm to solve a problem. Let's talk about it. So we can write a parallel runtime, that is T of P, as W plus T0 W comma P divided by P. So the resultant expression for your speed up is S is equal to W by TP, which will be is equal to WP divided by W plus T0 W of P. So finally we write an expression for efficiency as E is equal to S by P, which is equal to W upon W plus T0 W comma P. It is equal to 1 by 1 plus T0 W by P divided by W. So for our scalable parallel system, the efficiency can be maintained at a fixed value, say in between 0 to 1. If your ratio, that is T0 by W, is maintained at a constant value, that is, it is, at a constant value, it is maintained. So as a desired value E of efficiency, it is defined by is equal to E is equal to 1 upon 1 plus T0 W comma P divided by P. E stands for E T0 W comma P divided by W, which will be equal to 1 minus E upon E. So W is equal to 1 minus 1 by E upon 1 minus E T0 W of P. So if say we take that K is equal to E upon 1 minus E, which is a constant, which is depending on the efficiency of the maintained, that is, since T0 is a function of your T0, it's a function of W and P. So we have W is equal to K T0 W of P. So your problem size W can usually be obtained as a function of P, by manipulating your algorithmic to keep by algebraic manipulations to keep your efficiency constant, and this function is generally called as your isoefficiency function. So this isoefficiency function determines the ease with which a parallel system can maintain a constant efficiency and hence achieve a good speed up, which is increasing in proportion to the number of processing elements. That's it. Thank you.
Zeal Education Society, redefining excellence.